Welcome back. We are going to continue our lecture with the general properties, some few properties that we want to keep note of. What are these properties? The first one, the inductor current is periodic. So we are making the assumption that the inductor current is periodic. So that's the first assumption we want to make, or the first property of the current which is going to be flowing through the inductor. The average inductor voltage is going to be 0. And we know that when we have a periodic current, then the average voltage across the inductor is going to be 0. Similarly, the average capacitor current is also going to be 0. So the capacitor current instantaneously is not 0, but when you find it across one period, you find the average of that voltage, then we are saying that the average capacitor voltage is going to be 0 because it is also periodic. The fourth one, the power supplied by the source is the same as the power delivered to the load. So I'm making the assumption that all the switches are ideal, which means the MOSFET or the transistor and then the diode. So with the assumption that those are ideal, then all the power which is supplied by the source, we are making the assumption that that power is going to be delivered to the load. When we start looking at non-ideal cases, then basically the assumption is that the power supplied by the source is equal to the power absorbed by the load in addition to the losses. Some assumption for analyzing the buck converter. Some assumptions. So we are going to go back again, since this notes on a page is divided into 2 pages basically. So let's go back. Some assumptions we need to consider when analyzing the buck converter. So the inductor current is continuous. So we may already mention about this. That is a continuous current mode of operation. The capacitor current is very large. The capacitor itself is very large, and the output voltage is going to be held constant at a voltage of V0. Now, we are going to take a look at the effect when we make the assumption that the capacitor is not very large. But for now, we are going to assume that the capacitor is large enough that the output voltage across the load is a constant. The fourth one, the switching period is T, so we already mentioned that. So we are going to be switching the buck converter on and off. When the switch is closed, that time period is given by the duty ratio multiplied by the period, which is the T. And the time that the switch is open, that particular time period is given by 1 minus D times T. So those are the 2 times period we need to take off. Anytime the switch is closed and we are doing analysis, that time period is given by the duty ratio times T. And anytime the switch is open and we are doing analysis, that time period when the switch is open is given by 1 minus D, 1 minus the duty ratio multiplied by the period T. And the fifth assumption we want to emphasize is the components are ideal. So the transistor we are using for the switching is ideal, and the diode is also ideal. Two main key things to note, which we are going to use after we've done some analysis to try to find the relationship between the output voltage and the input voltage. And we could use any of those two. So 2 key analyses to note. The first one, the net change in inductor current over one complete period must be 0 for steady state operation. So we said we are operating in steady state. So since we are operating in steady state, it means that the net change in inductor current when the switch closes and then when the switch opens, that net change should be 0. If that net change is not 0, it means that the inductor current is going to keep increasing after every period or keep decreasing depending on the direction in which it's moving. So the net change has to be 0. The other analysis pertaining to the inductor, which we could use at the end to find the relationship after we've come up with some equation, is the average inductor voltage should be 0. If we are saying that we are operating this buck converter in a steady state operation, then the average inductor voltage should be 0. Now, why are we focusing on the inductor? The inductor in the buck converter is the main element for energy transfer. So that is the main element for energy transfer from the source to the load. That is why we are focusing on an inductor, to be able to find the relationship at the end between the output voltage and the input voltage using, if I grab my pen, using any of these two analysis notes that we've listed here. So the net change in inductor current of a period must be 0, and then the average inductor voltage is also going to be 0. Very good. Let's take a very quick analysis when the buck converter switch is closed. So we mentioned this before. So we said when the switch is closed, so this is where the switch was before. If I grab my pen, I can easily show you. So the switch was here. So when the switch is closed, then basically we have current which is going to flow, and the current over here is going to what? Is going to be 0, which is going to reverse bias our diode. So our diode is going to be open. So we are going to have the source current, which is IS, to be the same as the inductor current, which is IL. And then the current through the diode is going to be 0. The voltage across the inductor is given by what? The voltage at this node. This is open, right? So the voltage at this node is Vs. The voltage at this node is Vo. This is the voltage across the load. Since we are making the assumption that the capacitor is large enough, therefore Vo is constant, then the voltage across VL is going to be Vs minus Vo. So that is the voltage across the inductor, and we know the inductor law. The inductor law is given by L di dt. So from here we can find the I dt, where the L comes and divide. Let's go up to the next page. Now, before, let me mention something very briefly. So in this analysis we are doing, the switch is closed, and we know that when the switch is closed, that time period we are interested in, which is here, the T, is going to be given by the duty ratio D multiplied by the period. So I want to make that before we close out from this page. I also have a comment over here. Since we are dealing with a buck converter where the output voltage is always less than the input voltage, it means that Vs minus Vo, which is the same as the voltage across the inductor when the switch is closed, is always going to be positive. That is going to be greater than 0. This implies that the current through the inductor during the switch close operation is going to keep increasing. So if I grab my pen very quickly, it means if we sketch the current through the inductor when the switch is, let me do this again. If you sketch the current through the inductor when the switch is closed, then we are going to have current going up and down like that. Okay, so it's going to keep increasing when the switch is closed because the voltage across the inductor is positive. Let's go ahead and erase that. Now we have di dt, so on the previous page is equal to Vs Vo over L, which means the voltage across the inductor divided by L. We are going to make some substitution over here. So di dt, which is the rate, we can represent it as the same as the change in IL over the change in T, right? So that change in IL over the change in T is basically the same as the rate, di dt. So the change in T for that first period is given by dt, and we have the change in IL. This change in IL over dt is still given by Vs minus Vo over L. We want to find an expression for the change in the inductor current when the switch is closed. How do we get that one? We are going to make the change in RL the subject, and when we do that, we come out with this expression as we have over here. So change in RL when the switch is closed is given by the voltage across the inductor during that period divided by L, all multiplied by d dt, the dt ratio times the period. This gives you the change in the inductor current when the switch is closed. To show this graphically, let's close this one up. So inductor current goes up, comes down, right? So this is the period when it's closed, the first period here. So when the current goes up, so that is the change in the inductor current we are looking at, change in IL. Let's reduce that. So this is a change in IL that we are looking at, and the dt is the change over here, from here when the current starts going up till when the current reaches its peak, and that is going to give us the dt. Ratio of rise over run is the same as the gradient, and that is exactly what we are doing over here. That's exactly what we are doing over here. So when the switch is closed, the relationship between the change in inductor current and the period is given by this expression. Let's go ahead and erase that. Makes our notes a bit clean. Is given by this expression over here. We are going to go ahead and do another analysis for the change in inductor current when the switch is open. We are going to try to do that analysis. Now, for steady state operation, we expect the change in inductor current when the switch is closed to be the same as the change in inductor current when the switch is open, just that they should be in the opposite direction. One should be the negative of each other. Now, if the system is really in steady state, then when we add those two changes, it should give us 0. It should give us 0 to confirm that we are operating in steady state. We are going to end this lecture over here, and the next lecture is going to pick up from here. Thank you.